In this lab, I'm going to be talking about constant velocity. So the purpose of this lab is to record an object moving in constant velocity using Newton's second and extract data from a digital tracker to compare the real data of the object's movement with a computer model. Our assumptions in this case is that there are no air resistance, there are no forces applied on the object, and we want a vision where the object's movement is constant. The key principles to take in here are Newton's first law, which states that an object in motion will stay in motion unless acted upon by another force. And the same applies when the object is at rest. It will stay at rest unless acted upon by another force. We also used Newton's second law, which is most important here, as we modify it to get the velocity update formula and the position update formula shown here. We also have to note that acceleration can be written as F_net over m, which is essential in this experiment as we are defining F_net to be 0. And you must also note that velocity, force, and acceleration are vectors in this equation. The apparatus for our experiment is a table with a smooth, non-inclined surface with very small friction. It would be ideal to have a frictionless table, but since we don't have the material for our experiment, we used a table that has a very small friction. Our rolling object is also needed, and in this case we thought that it would be ideal to use a whiteboard marker. And we also used a ruler to keep track of displacement. Our initial variables are a time of 0 seconds and an initial position of 0 meters, and we use Python to generate the computer model. We also assume that the marker is moving solely in one direction, in this case being the X direction. So this is the video we recorded. Just please note that we flipped this video 90 degrees clockwise so that it shows the marker moving in the negative X direction for our purposes of this experiment. So the tracker stats are an initial position of 0, 0, 0. And we found the initial velocity by getting the change in X and the change in time in our tracker data. And we got an initial velocity of negative 0.417 meters per second in the X direction. So we did some modifications to our glow script, where the ball position, we put it as 0, and the ball velocity, we applied it here as a vector, and we put delta t as 0.01 to get as many accurate iterations about the repeating process of getting the velocity update and the position update, which is what we do in this while loop, which has a duration of what our tracker data recorded. And we assumed a F_net of 0 newtons, and the ball position, we were updating the ball velocity with the delta t value for the specified iterations. This gave us this computer data where we see how the ball initially started in this yellow small ball and moved towards the left, which is exactly the movement that we see in our video. Now, when we compare our data, we see something that is ideal for the purposes, but it explains how real-world data cannot be correctly interpreted by the computer when we assume that it is constant velocity. This is because there are some forces that we did not consider that are changing the slope of the real-life data, being the blue, that is not a perfect negative slope, which is what occurs when it's to the position graph when it is constant. Now, what if the x-axis was flipped? Well, in our experimental case, the tracker recorded the object moving in the negative x direction. Therefore, if we were to flip it, it would be moving in the x direction, thus moving the right positive direction. Thus, we would see that our position versus time graph would be moving in the same rates, same slope, but instead of going downwards, it would be going upwards. What does this mean? Well, can I determine net forces acting on the object? No, not really. In a computational model, I can make F_net equals 0. However, in real life, we have air resistance, friction, and gravitational forces that act on the marker by microscopic interaction between the near surface and the system. So in reality, it's really hard or nearly impossible to record a perfect experiment of constant motion with F_net equals 0 newtons, and there will always be a force acting on the object. So the error in this experiment is an error in the program, assuming that F_net equals 0, which is not really, and it's very hard to find a way to find what's the actual value of F_net, as it is probably always changing by the real life scenario. And it might have been improperly calibrated and not exact inputs applied to the tracker. My human error is that when I applied a force on the object, I probably did not do it in a sole perfect straight direction in a straight axis. And I also ignored gravity, air resistance, and friction in the experiment. Thank you.